I'm pleased to have with us Krystal Mejia, who is from CBS Interactive and who is going to talk about an event which used to take the most eyeballs in the US, which is the Super Bowl, from CBS Interactive. So please, you have the floor for 30 minutes.
Thank you. Hello, everyone. My name is Krystal Mejia. I'm a software engineer in the video technology group at CBS Interactive. More specifically, though, I work on the video processing team. We focus on processing, publishing workflows to really empower the 30-plus brands that fall under the CBS Interactive umbrella. But today I'm gonna talk to you about a very specific event we streamed back in February, Super Bowl 53, about how we engineered a live streaming workflow, but really more broadly, it's about how we do live streaming at scale at CBSI. So as I'm going through the slides here, here's kind of a high-level overview of what I'm going to be talking about. I'll basically take you through our whole video stack, starting with the signal acquisition and encoding, all the way through to delivery to the end clients. I'll talk a little bit about how we handled our advertisement using an eSAM integration. We'll talk about the monitoring tools we had, the sort of operational visibility we had on game day, our testing schedule, or really how we planned for failure to be prepared for any possible curveball that could be thrown our way on game day. And then we'll touch briefly about game day, how it all turned out. So when I'm talking about challenges, I'm really talking about challenges relative to where we were 3 years ago. So every year, Super Bowl switches networks. Since the last time we've had the Super Bowl, there's been a growth of devices, platforms in the market, exponential growth of viewers. Super Bowl is the biggest offender of this. Every year, it's breaking its own records. So we knew up front the sort of challenge it would be to scale our infrastructure to meet the audience demands of high quality. This time around, we were also taking full ownership of our end-to-end workflow. Previously, the last Super Bowl, we had different third parties, different vendors, managing different components of the infrastructure. This time around, we were building it all in-house, and with that, it's its own set of challenges, right? How do we monitor our infrastructure? How do we test this infrastructure? How do we ensure that we have the operational visibility to ensure that we were giving our users a good quality stream? And finally, communication and collaboration. That's kind of a gimme. Happy to be here, lucky to be here, but I'm one small piece of the puzzle. Truly, it takes a village to get a stream like this up and running. It's from ad ops to DevOps, broadcast teams, interactive teams, and it was important that we were all communicating and constantly collaborating during the planning and the testing of all this. So before we jump into the technical details, these are sort of what I see as the principles that guided us as we were planning and implementing the workflow. Do not over-engineer. It's a pretty basic engineering principle, but it was important that everyone understood not to add so much complexity to our workflow than what was needed. A huge thing for us was to eliminate single points of failure and to add redundancy as needed, but of course it's a balance. You don't want to add so much complexity that you've over-engineered this thing, you don't have the proper visibility or management of the infrastructure. And finally, planning for failure. This was really important for us that we had a pretty rigorous test schedule in place so that we could understand how all the components of the system worked, whether it was a domino effect or if it was an isolated failure. We wanted to be prepared on game day to know what was happening within our infrastructure. And really, when you sort of marry these principles together, it's to reach the overending goals, which is the user experience. We wanted to minimize impact to the users and optimize their experience. So before I start talking about this, though, so there's this dotted line going through the middle of the broadcast center that's just for me to differentiate between broadcast workflow and the OTT side of the workflow that the CBS Interactive team worked on. Everything to the left, the broadcast, is not necessarily up to scale. There's a lot of complexity, a lot of complex circuits being used here, but it is important to know, right? We had a satellite feed from the stadium. This was entered into the cord room where there was further processing. We had SCSI 104 markers injected. We had 608 captions embedded. And so effectively we have a 1080i feed being injected into these timecode card embedders, which is where our CBS Interactive workflow starts, the OTT half of the workflow. So we purchased these timecode cards so that we can, we synchronize them with the master clock in the broadcast center, and we injected linear timecode, and this was so that we could leverage the output locking functionality on the Elemental Live appliances. We used the on-prem appliances, and so what output locking does is it's synchronizing your streams as they're being delivered to the origin. So effectively, we have 4 streams, being delivered to our origins, we understand that the manifests are aligned, the segments are aligned, effectively giving us redundancy at our origin, per region, and per encoder. Another thing we did really differently with encoding this time is we used QVBR, the quality variable bitrate. So what QVBR does is it analyzes the complexity of your input, of your source, and then it's dynamically allocating bits based on that complexity. So it keeps you from wasting more bits than what is needed, and you get to save on costs, especially when you consider egress and bandwidth to the CDNs, right? So our ABR stack, we used H.264, 5 renditions. We maxed out at 720p 60, 6 megs. And as I said earlier, right, we wanted to eliminate single points of failure. We actually had a facility in Connecticut, which is a primary facility for CBS Sports, for the studios there. So we effectively just took one of the outputs from the timecode cards and routed those over to the facility via fiber. One thing I want to point out, though, is all 8 of these streams are not output locked and in sync with each other. We output locked per facility, so you have 4 streams in sync coming out of Connecticut and the primary facility in New York. So this is just a graph, visual representation of the sort of cost savings that we saw by implementing QVBR. You could see on the right here, it's per hour, but overall, we saw over 30% in savings on our highest renditions. And so for the advertising workflow, so as I mentioned earlier, we had SCUDdy 104s being injected out of the quarter room. We decided to bypass any server-side solutions and just burnt in the ads in the stream just to ensure reliability and delivery of the ads to those users. So effectively, we have a SCUDdy 104 being inserted into Elemental Live appliances. And what we did with our Elemental Live appliances is we took advantage of the ECM integration. So what happens is the Elemental Live encoders will convert the SCUDdy 104s into SCUDdy 35s. These 35s are then being thrown to the remote server where they are decoded, the ad ID extracted from the segmentation descriptor, and then that is repackaged in ID3 format and inserted back into the streams via the time metadata API on the encoder. And our reasoning for this is our players already had functionality for ID3 parsing. So this way our players can grab the ad IDs from the ID3 tags and register the impressions as needed. The biggest complexity with this integration, though, is your encoders expect a response from your ECM server within 10 frames. And we had issues where we just didn't have enough time to put this ECM locally to the encoders. Unfortunately, we had to do it in our data centers. And to avoid sort of this failover functionality where if the encoders don't get a response from your ECM server within 10 frames, it's going to fail over to a backup encoder or a backup ECM server. And then from there, if it doesn't get the proper response, it effectively stops trying to ping the remote server, and for us that would mean losing all of our advertisement impressions. So what we did is we actually deployed 4 servers for our ECM integration, 2 behind a virtual IP. Basically, these servers were weighted 99-1 behind the VIP, and then we were monitoring them in between ads and when we were back into content. So if there was an issue with one of the servers, we could just switch the weight so that we could keep our ad tracking workflow in place. So this is going to be like a PSA if you're using output locking and any sort of advertisement functionality here. I was going to show a video, but I just wasn't sure how it would show up on here, so I redrew the manifest. Let's assume these are 2 manifests coming out of 2 separate encoders that are output locked, and we're actually coming out of an ad break. I actually redrew this based on some test data that we had. I highlighted the program date timestamp so you can see they're effectively the same. In essence, you think these are aligned, but when you look a little deeper at the data, you'll see that the segments are actually not aligned. They're actually of different durations. And the reasoning for this is because we realized that our upstream, the trigger that was splicing the signals upstream, we were then injecting 2 separate signals, and they weren't exact splices. So it's important that you really try to use the same inputs when you're trying to use the output locking functionality, especially if you have any sort of advertisement or anything upstream that's splicing your feed. Okay, so now that we have our segments in our origin, we got to deliver them out to the end users, right? So we went with AWS Media Store Cloud Origin. It's a high-performant live origin. It has an extra layer on top that keeps segments hot in memory, which is really, really critical for live. We went with a multi-regional approach, so we could effectively balance the traffic between the east and west regions. And then when you go one layer above that, you have Fastly's Media Shield service. So we use this to protect our origins. The really neat thing that we did, though, with the Media Shield layer is implement automatic failover logic. So if there was HTTP errors, any timeouts, or manifest staleness, the Media Shield layer knew how to automatically fail over to a different origin and grab the segments from there. We also added some manual functionality so that if we had any issues with an encoder or a particular region, we could manually switch to a specific encoder or specific region within this Media Shield layer. One step above this, I've got Sidex's Open Mix platform. I'm actually going to show the backups real quick. So we actually had CloudFront as a backup layer, a backup Media Shield layer, and what the Sidex's Open Mix platform is doing here is just balancing between the primary and the backup path. Luckily, we didn't have to use CloudFront, but we did implement it, and the failover logics, we implemented that using the Lambda at Edge. For our Sidex's platforms, we actually use Route 53 as a manual backup. Luckily, we didn't have to use those as well. And then one layer above this, we have the Edge CDNs. I don't know why I didn't label them, so I'll give credit where credit is due. We worked with Fastly, CloudFront, CenturyLink Level 3, and Verizon EdgeCast. And so above that, you have Sidex's Open Mix, of course, doing the DNS-based switching of the CDNs. It's important to point out, though, from the Media Store origin to Media Shield to the Edge CDNs, we tried to use as many private network interconnects as possible to avoid having to use public transit at any point in time. So when you put it all together, you have a pretty simple diagram and workflow. But no, there's a lot of layers of complexity here, and with that, it's the challenge of how are we testing this infrastructure? What kind of visibility do we have over the infrastructure? And it's understanding identifying the points of failure and seeing how those all sort of, if there's a domino effect, or if it's an isolated failure or not. I'll talk a little bit more about testing here. So as I said earlier, we're trying to identify single points of failure or identifying any failures. And we did this just by simulating chaos to try to understand the domino effect or the downstream effect of what would happen if we effectively took out, if one of these components failed. So if I go back to this diagram, like say we take out one of the timecode card embedders, we went to the rack room, just pulled it right out to see effectively what would happen with everything downstream. And with this, we realize, hey, if we take out a timecode card, we're going to lose an encoder, and then we need a way to seamlessly take that encoder out of the stack, and we need a way to route traffic out of there. And so this is essentially, through these testing mechanisms or these stress tests, is how we essentially were able to implement our runbooks and our playbooks and understanding, what the downstream effect of all these systems was and how they would all sort of ricochet off of each other. These runbooks, and of course, everyone had their part to play. It was understanding what you needed to do, whether if you were on AdOps or DevOps, to ensure that you were properly triaging and fixing the issues when needed. A big thing we did was the minute we had full control of our infrastructure, we started streaming games through this infrastructure prior to the Super Bowl, and we would practice our failover logics when we were streaming these games in production. So we would effectively try to route traffic specifically to the East region, specifically to the West region, and this was just to ensure our confidence on game day that we knew how to effectively switch traffic and route it as needed. And of course, this is how our tooling for quickly making changes was born. Through all this testing, through understanding the behavior of our infrastructure, you can quickly create tools, command line tools to say, okay, we're going to just route traffic over to the east. But it's important that you understand the behavior of all the downstream effect and you effectively practice as much as possible. So for monitoring visibility, we've been using a lot of these in production for a while. On client-side QoE, we had Conviva, we had Mux. We've been using those for a while. We had TouchStream for synthetic monitoring, effectively monitoring our delivery side of the workflow. We actually worked with them to create a unified version that we can see, and I'll show a picture in a second, a screenshot. We use Sumo Logic for log collection and dashboards. For some internal tools, so we actually were checking manifest alignment to ensure that the segments as they were reaching the origin were correct. We created some dashboards around that. We had a multi-screen viewer so we could effectively visually see. It's a quick visual way of identifying any possible issues. So we were monitoring the inputs, we were monitoring all of our origins across both primary and backup facilities. And of course, we had Slack alerts. This was pretty effective for us, especially during testing. We had some alerts configured with our encoders, and we would do overnight tests where we would just test the network. We would pump out renditions running like 20 megs as much as possible to sort of stress test the network, and we could have these alerts running overnight to sort of understand the behavior of what was happening there. And so these are just this is dashboard screenshots of what we monitored on the encoding team. And so you have our sumo logic dashboards where we're checking for manifest staleness. And if you look at the two graphs on the bottom, you'll quickly see some spikes. In purple, that's in relation to the west region, and then when you sort of look at the graph where it's analyzing facility, you'll see that those blips to the west correlate with the Connecticut facility. This is a backup path, so it's a great way to say, hey, let's triple check the network in Connecticut, see why there's some latency maybe going to the west. I mean, these are small blips, so it wasn't necessarily important, but it's a quick way so that you can quickly identify and start triaging issues as they're happening. And then I have a picture of a monitor with our multi-screen viewer. So the first two rows are literally just monitoring the inputs. So if for whatever reason we lost an input, we would quickly see a slate and we could react before any impact to the end user. The next two rows are effectively monitoring our 8 origins, both from New York and Connecticut. And at the very bottom, we have the multi-CDN. And so these are some dashboards that the delivery team would have used. So at the very top, you have TouchStream. As I said, we worked with them to create sort of a unified view of, so we can monitor our origins. So you can see we're monitoring origins, and then from there we have the various media shields. We have the multi-CDN origins, and really all the edge CDNs. And at the bottom, this is all of the metrics coming out of the Radar platform for Sodexis when we were doing all the decisioning for CDNs. And then here we are at game day. So effectively, we had war rooms spread out across the US. In San Francisco, we had the delivery team. We had all of our CDN vendors available to us. They were on site with us so that we could quickly work with them, identifying any issues that may happen. In New York, close to the broadcast center, of course, we had the encoding team monitoring everything as we were delivering to our origins. And then in Florida, which is the CBS Sports headquarters, we were managing site infrastructure as well as some players. And then before I end the talk, I will give you an example of an issue we identified on game day, how we were able to triage what was happening. So we noticed some latency happening at a pop from Fastly over to the origins. Rather than try to identify the issue, we simply just routed the traffic over to the east region, and then we engaged Fastly and AWS sort of engaged to see what was happening, and that's when we realized some of our traffic was actually going over public transit as opposed to the private network interconnects. And so once the issue was fixed, we were able to route traffic back without any impact to the users. And that's the end of my talk. Thank you, everyone.
So, thank you very much. So, I assume we have questions. Irash, you want to give the question to somebody who didn't ask question? Somebody else than Irash. You will get your question last. No? Okay, Irash, you got your question.
So I don't know whether you can disclose the second part of my question. What was the latency end-to-end, and what was the top, highest number of clients you had in point in the...
I cannot disclose that.
Latency?
On latency, so you showed a graph yesterday. It was about 28 seconds on your graph, and that's about right. And it was different between our OTT platforms and our desktop.
You should ask me the question. So Maybe one question, you mentioned you cannot disclose the scalability. Could you tell us how many CDN were active during your several?
We had 4 CDNs.
4
we worked
CDN.
with. Mhm.
And ordered or more like balancing one versus the other?
Yeah, I mean, so we were we had radar from Sodexis. They would come with some measurements based on throughput, availability. We also based decisioning on capacity limits. So if we had reservations with all our CDNs, and if we were getting close to our capacity limits, we would route to a different CDN.
So you reach maximum capacity, some.
I'm not sure if we did on any specific CDN or not. I know that's the functionality that I was working with, but I'm not privy to whether or not we did hit those limits or not. I just know that that's the functionality.
Okay. Thank you very much. Thank you for your talk, and please.
Thank you.
Krystal.